In this video tutorial, I'll show you how to represent positive and negative numbers using signed magnitude binary bytes. The previous videos showed you how to do this for a binary nibble. Here we're going to look at it for a binary byte. The previous video in the playlist shows you how to represent a positive and negative number using a binary nibble. This video is going to ask you to apply the principles that you learned there to perform A and B, where A says represent plus 29 by a signed magnitude binary byte, not a nibble but a byte. B asks you to do the same thing, but on this occasion it says represent minus 29 by a signed magnitude binary byte. Pause the video and have a go at this yourself by using the approach you saw in the last video. Once you've had a go, restart the video and I will go through the solution. Let's consider A, where it says represent plus 29 by a signed magnitude binary byte. Well, we start off with 29 and we ask how many times does 2 go into 29, and the answer is 14 with a remainder of 1. We then ask how many times 2 goes into 14, and the answer is 7 times, and on this occasion there is no remainder because 2 goes into 14 exactly. Then we ask how many times does 2 go into 7, and the answer is 3 times with a remainder of 1. We then ask how many times 2 goes into 3, and the answer is it goes once with the remainder of 1. And then we ask how many times does 2 go into 1, and the answer it doesn't, and that 1 is then remaining. The division process stops when we have a 0 in this position. And now we can turn our attention to the remainders. And I'm now going to write out what 29 equals, as you can see it appearing now. And this 29 is represented in binary as you see here. This least significant bit is placed here. This is placed in this position, and we can see that the colours inform us where the bits appear because this is the most significant bit and it appears here in the number. What I'm going to do is to remove the colour as you see here, and if you look at this binary pattern you can see there's only 5 bits. Now I have to have 8 bits in order to represent plus 29 by a signed magnitude binary byte. So if you look here you can see that I've added in this position 3 zeros in the most significant position, and those 3 zeros therefore don't have any value. So this binary pattern represents 29 in the same way this represents 29, but the fact that I've put these here means that overall we have a byte. Let's focus on the binary byte for the 29. We could simply say, well look, this is an example of an unsigned binary pattern because I haven't given any consideration to the sign bit yet, and this would represent 29. However, what I'm going to do, I'm going to place the pattern as you see here in 8 flip-flops. Now what I wish to do is to reflect where the sign bit is going to be, and you can see I've shaded that in the yellow background. And this is the sign bit, and because it's 0, it's positive. Now the remaining bits, and there are 7 of them, that's the magnitude, and they form 29. Consequently, we can see that this is plus 29 because this sign bit represents this positive, and these represent the magnitude, which is 29. Let's now consider B, where we have to represent minus 29 by a signed magnitude binary byte. Well, the first thing we need to do is to consider how we represented plus 29. And it's very easy to produce minus 29. What you do is shown here. And you can see that the magnitude here has simply been placed in this position, whereas if you look at this sign bit, which is positive, we've changed that to 1, which represents negative. Consequently, this represents the negative and this represents the magnitude, which is 29. So if we now concentrate on this, what we've got this being the sign bit, and because it's 1, it's negative. This being 29, and of course all of this byte then will represent minus 29. Let's consider an unsigned binary byte, and here's an example here where everything is zeros. And of course we can carry on and put different combinations of ones and zeros in until we eventually get to where everything is all ones. And what you have here are 256 combinations, and every combination will represent a number. There's no sign bit in this representation here. Consequently, the first one is 0 and the last one is 255. So the range goes from 0 to 255, 256 combinations in total. Let's have a look at the number line associated with an unsigned binary byte. We know we can mark the beginning of the line off as 0, and further along we can mark it off as 255. Now we can represent the 0 position by this binary pattern where we have 8 zeros, and we can represent 255 where we have 8 ones. And in between we have all of the other combinations representing other positions on the number line, 1, 2, 3, etc. And in total there are 256 combinations of the binary pattern. So we can represent 0, 1, 2, 3, 253, 254, 255. So we can represent all values along the number line, but with no fractions, just whole numbers as we go up. And of course, if it's unsigned, we cannot represent any negative numbers. Let's now consider signed magnitude binary bytes, and let's have a look at the positive range. Now this is the value we have at the beginning, and if we carry on we have all of the other combinations, and this is the value we can have at the end. Now you can see that we don't go on to where it's all ones because we have the sign bit, and the sign bit is positive. So if we look at the first one, this is plus 0. This is the sign bit, which gives us the positive sign. This is the magnitude, which gives us the 0. If we look at this one, it gives us plus 127. This is the sign bit, which gives us positive. This is the magnitude, which is 127. So we can see that the positive range goes from 0 to 127. If we carry on, we can look at signed magnitude binary bytes again, but on this occasion let's have a look at the negative range. Well, that's where I have this, and if you look here you can see we have the sign bit being a 1, meaning a negative, and we can carry on to this combination where you can see the sign bit is still a 1 and everything else is now a 1. So if you look at the shaded yellow area, you can see that represents the sign bit for negative values. If we look at the first one, that's minus 0, because this is the negative as shown here. This is the magnitude, which is 0, so we can see that this gives us minus 0. Whereas if you look at this, you can see this is minus 127. This gives us the negative, this gives us the magnitude, which is 127. So overall this gives us minus 127. Let's consider the number line for signed magnitude binary bytes, and we know we can mark this off as a 0. Now the maximum positive value we can have is plus 127, and the most negative value we can have is minus 127. If we look at the binary pattern that represents plus 127, we can see it is here, and there's the sign bit, and here you can see we have the magnitude, which is 127. And if we have a look at minus 127, it's shown here. There's the magnitude of 127, and this is the sign bit, meaning negative. If we now consider the 0, well, we can represent the 0 with 8 zeros, as you can see here. But we also have found that we can represent the 0 as shown here, and it's clear that you've got a sign bit here which is negative. So the 0 can be represented by plus 0 and minus 0. Now mathematically you may want to think about having a plus 0 and a minus 0, but from a computer science viewpoint, what we have with signed magnitude binary bytes is the fact that 0 can be represented by one of two codes, whereas every other number on this line that has a representation representation has a unique code. So this is a drawback. We can't have a situation whereby we have a position, in this case 0, having one of two codes to represent it. The other thing we need to concern ourselves with is the fact that the number of combinations that can be represented by signed binary bytes is, as you can see appearing now, 255 combinations. Now that's because we have two of the combinations for 0. And we saw the same problem when we dealt with a nibble. We had one less combination than you would have if you had unsigned, and also we had the problem having two values representing 0. Now if you went to 16 bits, you would find you would have two representations of 0 there when you're using signed magnitude binary. Consequently, historically it's good to know about signed magnitude binary bytes, but in reality they're not used anymore within the arithmetic and logic unit of central processing unit because of this issue with having two codes representing 0. You will see that modern central processing units use 2's complement, which I'll be coming on to in due course. Please consider subscribing to the channel and click the bell to ensure you get an update every time I upload a video. Maybe you would like to consider supporting the development of these free videos via Patreon. In addition, why not follow me on Twitter and also check out the supporting website.